Quantum leap. Princeton physicists successfully entangle individual molecules for the first time. In work that could lead to more robust quantum computing, Princeton researchers have succeeded in forcing molecules into quantum entanglement. For the first time, a team of Princeton physicists has been able to link together individual molecules into special states that are quantum mechanically entangled. In these bizarre states, the molecules remain correlated with each other, and can interact simultaneously, even if they are miles apart, or indeed, even if they occupy opposite ends of the universe. This research was published in the journal Science. Molecular entanglement, a breakthrough for practical applications. This is a breakthrough in the world of molecules because of the fundamental importance of quantum entanglement, said Lawrence Chuck, assistant professor of physics at Princeton University and the senior author of the paper. But it is also a breakthrough for practical applications because entangled molecules can be the building blocks for many future applications. These include, for example, quantum computers that can solve certain problems much faster than conventional computers, quantum simulators that can model complex materials whose behaviors are difficult to model, and quantum sensors that can measure faster than their traditional counterparts. One of the motivations in doing quantum science is that in the practical world, it turns out that if you harness the laws of quantum mechanics, you can do a lot better in many areas, said Connor Holland, a graduate student in the physics department and a co-author on the work. The ability of quantum devices to outperform classical ones is known as quantum advantage. And at the core of quantum advantage are the principles of superposition and quantum entanglement. While a classical computer bit can assume the value of either 0 or 1, quantum bits, called qubits, can simultaneously be in a superposition of 0 and 1. The latter concept, entanglement, is a major cornerstone of quantum mechanics, and occurs when two particles become inextricably linked with each other so that this link persists, even if one particle is light-years away from the other particle. It is the phenomenon that Albert Einstein, who at first questioned its validity, described as spooky action at a distance. Since then, physicists have demonstrated that entanglement is, in fact, an accurate description of the physical world and how reality is structured. Challenges and advances in quantum entanglement. Quantum entanglement is a fundamental concept, said Chuck, but it is also the key ingredient that bestows quantum advantage. But building quantum advantage and achieving controllable quantum entanglement remains a challenge, not least because engineers and scientists are still unclear about which physical platform is best for creating qubits. In the past decades, many different technologies, such as trapped ions, photons, superconducting circuits, to name only a few, have been explored as candidates for quantum computers and devices. The optimal quantum system or qubit platform could very well depend on the specific application. Until this experiment, however, molecules had long defied controllable quantum entanglement. But Chuck and his colleagues found a way, through careful manipulation in the laboratory, to control individual molecules and coax them into these interlocking quantum states. They also believed that molecules have certain advantages over atoms, for example, that made them especially well suited for certain applications in quantum information processing and quantum simulation of complex materials. Compared to atoms, for example, molecules have more quantum degrees of freedom and can interact in new ways. What this means, in practical terms, is that there are new ways of storing and processing quantum information, said UK Liu, a graduate student in electrical and computer engineering and a co-author of the paper. For example, a molecule can vibrate and rotate in multiple modes. So, you can use two of these modes to encode a qubit. If the molecular species is polar, two molecules can interact even when spatially separated. Nonetheless, molecules have proven notoriously difficult to control in the laboratory because of their complexity. The very degrees of freedom that make them attractive also make them hard to control, or corral, in laboratory settings.